Hello everyone, welcome to this week's algebraic graph theory seminar. Today, Lorenzo Ciardo from University of Oxford will tell us about Alice Bob and the colors algebraic approach to quantum advantage. Lorenzo, please.
Thanks a lot. Thank you very much for the invitation. It's very nice to be back in Waterloo, at least virtually. I was there during my master's for a semester and had a very good time. So I want to start with introducing the object of the talk, which is graph coloring. Right? So this is a classic problems in graph theory. I have a graph. I have a set of vertices, and I want to assign a color to every vertex in a way that whenever I have two adjacent vertices, they get distinct colors. Right? So, for example, something like this. So this is the same as finding a homomorphism. So a edge preserving map from the vertices of X to the vertices of K3, so or Kn, so the complete graph having n vertices. And then this allows me to generalize this to any graph instead of the complete graph, right? So I can replace Kn with any graph Y and test whether X is homomorphic to Y. Okay, in fact, even more in general, I cannot limit myself to graphs, but I can consider arbitrary relational structures, which means that instead of having just a unique relation, the edge relation, which is binary, I can imagine to have multiple relations with arbitrary arities. This is not going to be super important. We can actually focus on graphs here, but allowing this generality allows to capture via homomorphism problems the whole class of constraint satisfaction problems, CSPs, right? So these are problems such as I give you X as an input, and I'd like you to answer yes if X is homomorphic to Y, and no if X is not homomorphic to Y. Right, so here I imagine Y to be fixed, to be the template. So for example, if Y is the clique, I get, again, graph coloring, right? So the CSP of the clique having n vertices is exactly graph n coloring, but I can express in this framework many more problems, such as linear equations, mod P, which is the CSP corresponding to some structure encoding all hyperplanes of ZP, or a lot of Boolean satisfiability problems from logic. Okay, so this is the main object, the main character, and now we can start the story. And the story may start in 1971 with the introduction of the concept of NP completeness by Cook. This somehow revolutionized the way we look at complexity because it allowed to see many problems that are seemingly unrelated. It allowed to see them having the same complexity, right? So for example, problems such as SAT, clique, graph coloring, even if they are seemingly unrelated, they all have the same complexity, which is NP complete. And people started to realize that many problems are NP complete, many problems are solvable in P, but the problems that are not NP complete and not in P, but intermediate are, even if they do exist, unless P is equal to NP, they are much less natural. So in particular, for problems such as Boolean CSPs, so homomorphism problems where I only have two elements, two values, 0, 1, or homomorphism problems on graphs, this never happens. So these problems are either in P or NP complete. Is it true that all CSPs exhibit this dichotomy? Well, somehow until the end of the century, there were no tools to actually study at this level of generality, this question. But the tools appeared at the end of the century, 1998, we can say. So CSP complexity was found to be governed by some invariants, algebraic invariants of the problem that are called polymorphisms. I will later say a bit more about them. So this opened a new era in CSP theory, the algebraic theory of CSPs, that eventually culminated in the proof by Bulatov and Zhuk of the CSP dichotomy theorem. So it is true, but for the whole class of constraint satisfaction problems, so for the whole class of homomorphism problems, that the problem is either in P or NP complete. Okay, so this was a nice story, but somehow it's not the story I want to tell today. So I want to actually redefine graph coloring a little bit. So I want to define it as a game now. So consider now the situation in which we have two players, Alice and Bob, and a verifier. So Alice and Bob are questioned by the verifier, and their goal is to convince the verifier that a given graph is n-colorable, so can be colored via n colors. Okay, so first Alice and Bob strategize. They think about some strategy, and then when the game starts, Alice and Bob are separated. They cannot communicate anymore. The verifier asks a question to Alice: what's the color of a vertex XA? And Alice replies, for example, with red. Then the verifier asks Bob a question. So what's the color of XB? And Bob replies with maybe red again. Okay, so Alice and Bob win if they reply with equal colors whenever they get the same question, and when they reply with distinct colors whenever they get adjacent vertices. Okay, it's not very hard to see that this actually captures what we mean by n-coloring, right? So what is a strategy? Well, a deterministic strategy is going to be a function that takes vertices of x and assign to them colors. So the vertices are the question and the colors are the answer. And the strategy is perfect whenever the function is actually an n-coloring, right? So the second condition is telling me that whenever I get adjacent vertices, they should get distinct colors. So this is just another way of defining n-coloring. This also for arbitrary graphs. In fact, by changing a little bit the game, we can extend this to arbitrary relational structures, right? So a homomorphism from X to Y, or a yes instance of CSP of Y, is just a perfect, so winning classical strategy for this game. Okay, suppose now that Alice and Bob really want to win the game. So they study quantum mechanics and they find out about entanglement, which essentially means that there can be correlations between particles that are stronger than classical ones. So at a very intuitive and basic level, if I have two particles that form that are in a non-entangled state, I can describe individually each of them as a vector in a Hilbert space, and if I measure one, the outcome is not going to impact the state of the second particle, and this is mathematically because, well, the state of the bipartite system is a product state, so it's a tensor product between the individual states. But, well, the tensor product of two Hilbert states is bigger than the set of all tensor products of states living in the individual spaces, which means that I can also have entangled state. The property that if I measure a system A, the outcome I get is going to have some correlation with the state of B. Okay, so can Alice and Bob use this correlation? Can they use entanglement to actually win the game of colors, even if classically they should not be allowed to win it? Okay, so let's play again the game, this time in the quantum world. So the game is similar. There's a strategy phase. Now Alice and Bob are allowed to share entanglement in the strategy phase. And then the game starts and they are separated. And this is expressed by the fact that Alice can only measure her part of the system and Bob can only measure his part of the system. So the question is again the same, what's the color of XA? And Alice, before answering, she measures her part of the state, right? So she measures the state via a measurement depending on the question, and she sees that the measurement gives red. So she replies red. And the verifier asks Bob a question, now what's the color of XB? And well, if the state is properly entangled, chances are that Bob now will see his state to be blue. So he will reply blue. The winning condition is again the same. And now, well, what is a strategy? It's going to be a function that takes vertices of the graph and returns projection valued measurements, right? So for every question of the verifier, I have a measurement. The index of the measurement outcomes correspond to colors. So they are the replies of the players. A perfect strategy is a quantum strategy that satisfies the winning condition, and we can call it a quantum coloring, or more in general, a quantum homomorphism. Right? So for the quantum coloring case, this was defined by Cameron and others, 2009, I think. It was later generalized to arbitrary graph by Manziska-Robertson and to arbitrary relational structures by Abramsky et al. Okay, so when is entanglement necessary for winning the game? When is it the case that I cannot win classically, but I can win by a quantum entanglement? So we define Y to have quantum advantage over some Hilbert space H if there exists some X such that the game corresponding to X and Y can be won using entanglement over H, right? So the measurements are over H, but there is no perfect classical strategy. So this is also known as pseudo-telepathy or Bell scenario, and it gives a proof, at least in an abstract way, it gives a proof of the non-compatibility between quantum and classical physics. Okay, so let's go back to the story and let's start another story. This one starts in 1964. When Bell showed that quantum mechanics is not compatible with any theory of physics which is local and realistic. Well, local means that the outcome of, or the choice of Alice's measurement does not impact on the outcome of Bob's measurement. And realistic means that the outcome of a measurement is completely described by the measurement device and the system that I'm measuring. So there are many proofs of this theorem, which is a fundamental theorem of quantum mechanics. Let me just say that I want to see this as an analog of the concept of NP completeness in the first story. So among the many proofs, each proof corresponds to a game in a sense. So the Cauchy-Specker game, the CHSH inequality, GHZ game, Magic Square, they are all different games exhibiting quantum advantage. In some of them, quantum advantage is different from the definition I gave, in the sense that there is no perfect entangled strategy. There is just a better winning probability if I use entanglement, but essentially the principle is the same. So some partial classifications of quantum advantage were found later for some classes of games, Boolean games or XOR games, but somehow there is no clear unified approach. And now I want to argue that somehow the same object that captures the first story can be used to tell us something about the second story. Okay, let me first give a very short introduction to the algebraic CSP theory, right? So remember that a CSP, so the CSP parameterized by some Y, you can think of Y to be the n-clique, for example. So this is the following problem. I give you X as input. I want you to answer yes, is fx homomorphic to Y and no otherwise. So the key object, as I said, of CSP theory is the notion of polymorphism, which is actually a very simple notion. It is just a homomorphism from some power of Y. So this is the direct power or the categorical power of Y to itself. That's it. So for example, let's look at free coloring, right? So this is the CSP parameterized by the free clique, the triangle. What is a polymorphism of free coloring? Well, it's going to be a homomorphism from some power of K3. So for example, K3 square, which is this graph here, to K3. Or in other words, it's just a free coloring of this bigger graph here. Okay, so let's try to free color this graph. There is, for example, this option here. Arrange the colors vertically. There is an option of arranging them horizontally, but we quickly see that there are not many options. So the polymorphisms of free coloring are very limited, and their structure is very clear. They are all projections, which means that I am just projecting on some coordinate. And this is essentially the reason why free coloring is NP complete. Right? So the complexity of a CSP is entirely determined by the set of its polymorphism. And if the polymorphisms are trivial, in a sense that I only have projections as polymorphism, essentially, or something that can be derived from them, then the CSP is NP complete. If the polymorphisms are non-trivial, so if there is some interesting polymorphism, so some interesting coloring of the bigger power graph, then the CSP is tractable. And polymorphisms capture the complexity of CSPs even at a finer grain. So if the polymorphisms of Y are a subset of the polymorphisms of Y prime, then the CSP of Y prime reduces in polynomial time, in fact, log space to the CSP of Y. And now I want to be a bit more precise here. So this is a notion of minion. So a minion is a functor from the category of non-empty finite sets to the category of sets. A bit more concretely, I have some objects, so a union of n-ary objects, and then some operations that are called minor maps. So for every map pi from n to m, I have a corresponding minor map. So it's not hard to see that the polymorphisms of a CSP form a minion. So they can be endowed with this algebraic structure. This allows me to compare two polymorphism sets, right? So a minion homomorphism is just a natural transformation between these two functors, which means that actually I have a way to compare the polymorphisms of Y to the polymorphisms of Y prime. In case there exists a minion homomorphism between the two, the second reduces to the first. And finally, it is possible to associate to every algorithm a corresponding minion such that the minion of the algorithm maps, so it meets a minion homomorphism to the polymorphisms precisely when I can use the algorithm to solve the problem. Right? So some of this was very fast and a bit abstract, but this is essentially the core of the algebraic approach to CSPs. We can study CSPs not by finding ad hoc reductions or reasoning in terms of Turing machines, but reasoning in terms of the algebra formed by the polymorphisms. Okay, can we do something similar for quantum advantage? Can we study quantum advantage via these polymorphisms? And it turns out that we actually can. So it is possible to define a quantum minion as follows. So consider a Hilbert space H. So it's going to be the space where my measurements live. Consider the set L of H of all linear subspaces of H. And then define the quantum minion as follows. So the objects are going to be vectors whose entries are subspaces. The two different entries must be orthogonal, and the sum of all of them as vector spaces must be the whole Hilbert space H. And then the minor maps are just given in terms of sums of linear subspaces. Right? So this is an example. This is an element of my minion. So I have three spaces that sum up to the whole three-dimensional space. This is a minor that associates 1 to 1, 2 to 3, 3 to 3. And the minor map is just this one. So it leaves the first element untouched. And it combines the second and the third in a two-dimensional plane. Okay, so this is again a geometric object, and it turns out that this completely captures the presence of quantum advantage. So a structure Y, for example, a graph, has quantum advantage over a space H, precisely when there is no homomorphism from the quantum minion to the polymorphism minion. Okay, so the proofing, I will not give the proof of this, but the ingredients are the quantum monad defined by Abramsky and others, the free structures defined by Bartobul, Krokin-Opshel, and minion tests defined by Givny and myself. The key point of this is that this shows that the occurrence of quantum advantage in a game is entirely determined by the polymorphisms of the game. Right? So we can use the same mathematical object, the same algebraic object, which is the polymorphism set, to study not just the complexity of the CSP, but also the occurrence of quantum advantage in the game. So let's see how to actually use it. And let's see this by comparing the quantum minion with two classical minions. So the first is the dictator minion. So this is a minion that has a very simple definition. So its n-ary elements are just the numbers from 1 to n, and the minors, so I minor pi is just pi applied to I. But the important thing is that this is the least element of the minion homomorphism preorder. So this minion here maps to every other minion. And because of the CSP dichotomy theorem, it holds that a CSP is NP-complete precisely when the polymorphism minion of the CSP admits a homomorphism to the dictator minion, right? So the CSP is NP-complete if the polymorphism minion is actually homomorphically equivalent to the dictator, and otherwise it is tractable in polynomial time. So this minion exactly captures what I said before about being trivial. Okay. Another minion. So this is called the semi-definite programming minion. It's a minion whose objects are matrices of some finite size, such that if I multiply it times the transpose, what I get is a diagonal matrix of trace 1. Or in other words, all rows are mutually orthogonal, and the norms of the rows sum up to 1. And well, the property of this is that it precisely captures what it means for a CSP to be solvable by the semi-definite programming algorithm. Right? So this minion here admits a homomorphism to the polymorphism of a CSP, precisely when the CSP is solvable by semi-definite programming. This was shown independently by me and Jivni and Braken Seguroswamy Sandeep. And this is known to be equivalent to the CSP having so-called bounded width, so being solvable via local consistency means. This was shown by Barto and Kojic. Okay, so how do these minions relate with the quantum minion? Well, one can show that the quantum minion admits a homomorphism to the dictator minion precisely if the dimension is 1 or 2. Or in other words, whenever the dimension of the Hilbert space is at least 3, the quantum minion is fundamentally different from this dictator minion. And also, one can show that for every Hilbert space, there is a homomorphism from the quantum minion to the semi-definite programming minion. Okay, so again, the ingredients of this, well, the first statement uses two facts. The first fact is a simple geometric object called the Hopf vibration of CP1 into the two-sphere. Right? So it's just a map that allows you to map orthogonal vectors into antipodal points of the sphere. This gives one direction of this gives the if direction, and then the only if direction comes from Gleason's theorem, which is a characterization of all measures of Hilbert spaces on dimension at least 3. And the reason why the theorem does not hold in dimension 1 or 2 is that Gleason's theorem only holds from dimension 3. Okay, and finally, the second statement is relies essentially on a complex version of this semi-definite programming minion that I defined before. Okay, so using this, so a simple corollary of this is that well, if the dimension of a Hilbert space is 1 or 2, I never have quantum advantage. This was actually already known. Using qubits, I can never get quantum advantage. But if the dimension is at least 3, then a graph has quantum advantage over the Hilbert space precisely when it is non-bipartite. So this is a question posed in a paper by Manziska Robertson. And the proof is essentially trivial from the theorem. So if Y is non-bipartite, then we know that the CSP is NP-complete. This is a classic theorem by Hell-Negetriel. But then we know that the polymorphisms map to the dictator minion, and then we can just compose with this theorem here to show that the quantum minion does not map to the polymorphisms, and we have done. On the other hand, if Y is bipartite, then the CSP can be solved by semi-definite programming or by a local consistency, which means that the SDP minion maps to polo Y. And again, composing with the homomorphisms here, we can show that it follows that the quantum minion maps to the polymorphism minion, and then we have no quantum advantage. Okay, so this was the first part of the talk. maybe before continuing, are there any questions on this? Okay, then I can continue to the second part, which is about the quantum chromatic number. Okay, so what is the chromatic number of a graph? Well, it is the minimum number, the minimum integer, such that the graph admits a homomorphism to the n-clique. Right? So the minimum n such that the graph is n-colorable. One can then define the quantum chromatic number as the same thing, but when I consider quantum colorings instead of classical ones, right? So in particular, I'm going to index the quantum chromatic number via D, which is the dimension of the Hilbert space, right? So chi D of X is going to be the minimum n, such that X admits a quantum homomorphism over CD to Kn. This is a notion defined by Cameron, Montanaro, Newman, Severini, Winter. All right, so, well, every classical strategy can be seen as a quantum strategy, right? So it is never possible to lose power by considering entanglement, of course, which means that the quantum chromatic number is never bigger than the classical one. But of course, you can ask, what is the maximum gap between the two? What is the maximum gap between KD, chi D and chi? Okay, so I'm going to first tell you some results, and then in the next slides, I'm going to say something about the proofs. So the first result is that for every D, so for every dimension D and every N, at least 3, there is a graph such that the D-dimensional quantum chromatic number is at most N, but the classical chromatic number is at least 2N minus 1. So this means that we fix D, which we can see as the number of qubits, right? So with a fixed number of qubits, the gap between the quantum and the classical chromatic number is at least 2, right? So there's at least a linear gap between the two. If I fix the number of qubits. On the other hand, I can ask what happens if the number of qubits is unlimited, or equivalently, if I can use entanglement over arbitrarily large dimensional Hilbert spaces. So here it is known that there is an exponential gap, right? So this follows from a theorem by Brassard, Cleve, and Tapp, Avis et al., and then a theorem on the classical chromatic number of Hadamard graphs by Frankel, Rodel. So there is a family of Hadamard graphs, an infinite family, and an infinite family of integers, of positive integers, such that the chromatic number of these graphs grows exponentially in the quantum chromatic number. But here the key point is that the dimension of the Hilbert space is also growing. So if I allow the number of qubits to be unlimited, then there is at least an exponential gap. And the last theorem I want to mention is the following. So conditional to a quantum advantage version of two facts from hardness of approximation, or CSPs, in particular Cotes D21 games conjecture and Hosted's inapproximability of linear equations. I will tell more about this later. So conditional to these conjectures here, the gap is unbounded. So it is possible to find graphs whose quantum chromatic number is 3 or 4, but whose classical chromatic number is arbitrarily large. Okay, so how I'm going to prove these facts here? Well, it is helpful to consider an extension of the notion of quantum advantage for pairs of structures. What do I mean by this? Well, suppose that I have some structure Y, for example, a clique, and suppose that Y has quantum advantage. Right? So what does it mean? Well, this means that if I have a perfect quantum strategy from X to Y, this is not enough to give me the complete classical information that X is classically homomorphic to Y. This is the definition of quantum advantage. On the other hand, it may be possible that a perfect quantum strategy at least gives me some partial classical information. Right? So is it possible that whenever I have a perfect quantum strategy from X to Y, I have a classical homomorphism, so classical perfect strategy from X to Y prime for a different structure y prime. So this gives a notional quantum advantage for pairs of structures. So a pair y prime has quantum advantage over H if there exists some X such that X admits a quantum homomorphism to Y, but X does not admit a classical homomorphism to Y prime. In other words, y prime has quantum advantage if the answer to the previous question is no. Okay, so this definition has a complexity counterpart, which is the notion of promise constraint satisfaction problems. This is a notion defined by Ostring, Guruswamy, Hostad, Rakesi, Guruswamy, Bartobulin, Krokin, Opschel some years ago as a generalization of CSPs, in particular as a way to capture algebraically a notion of CSP approximation. Okay, so what is the definition of a promised CSP? Well, I have now two structures in the template, y and y prime, for example, two graphs. And the problem is the following. So I give you some x as the input, and I'd like you to answer yes if x admits a homomorphism to y, and no if x does not even admit a homomorphism to y prime. Notice that for this to make sense, I actually want that y admits a homomorphism to y prime. Okay, so the key fact is that we can define polymorphisms also for this extended version of CSPs, right? So a polymorphism is just going to be a homomorphism from the nth power of y to y prime. And also in this setting here, the complexity of this problem is completely determined by polymorphisms. Right? So the complexity of PCSP of y prime is completely determined by the polymorphisms of y prime. Okay, so let's see some examples of this. The main example of promise CSP is approximate graph coloring. So here, my two structures in the template, so my y and y prime are just cliques, right? So kn prime for some n smaller than or equal to n prime. And this is the following problem. So I give you a graph. I'd like you to decide whether the graph is, let's say, 3 colorable or is not even 4 colorable. Now, what is the motivation under this? Well, we know that graph coloring is NP complete. So we can try to make the problem easier to see if it is, if it becomes tractable by not asking whether the graph is 3 colorable or not, but whether the graph is 3 colorable or not even 4 colorable, which is potentially an easier task. So what is the complexity of this problem here? Well, in this case, 3 versus 4, it is known to be NP complete, but for example, already 3 versus 6, the complexity is unknown. So this is a very popular open problem in classical complexity theory. Okay, so as I said, the complexity of these problems here are captured by polymorphisms, right? So what is a polymorphism for approximate graph coloring? Well, it is a 4 coloring, in this case, of K3 power 2, right? So I want to color this big graph here using 4 colors. And well, in the case before, so if here I had a triangle, as I said, the colorings are very constrained. But if I have 4 colors, I can have more choices here, right? So this is essentially the reason why studying the complexity of these problems is harder. I have more space for building polymorphism. So this is, for example, an example of a 4 coloring of K3 square. Okay, so why am I talking about this? Well, it turns out that we can study quantum advantage for pairs of structures by using the same tools as quantum advantage for single structures, right? So essentially, the whole facts that I mentioned before keep holding for this more general setting. So a pair y prime has quantum advantage over H precisely when there is no minion homomorphism from the quantum minion to the polymorphisms. And using this, we can reprove the same statements as before. So if the dimension of the space is at most 2, I never have quantum advantage. If the polymorphisms are trivial, so if they map to the dictator minion, I always have quantum advantage if the dimension is at least 3. If the problem is solvable via semi-definite programming, I never have quantum advantage. Okay, so we can use essentially the same theory also for this more general notion of quantum advantage. Now, why am I mentioning this to talk about the quantum chromatic gap? Well, the presence of an n versus n prime gap between the quantum chromatic number and the classical chromatic number is the same as saying that there exists a graph whose quantum chromatic number is at most at most n, but whose classical chromatic number is at least n prime plus 1. And this is exactly the same as saying that the pair kn prime has quantum advantage over CD. But then we know by the previous theorem that we can study this latter statement by using polymorphisms. So this gives a way to connect the quantum chromatic gap with the complexity of approximate graph coloring. Right? So using polymorphisms, we can essentially study these two things together rather than separately. And now let me go back to the story. So it was conjectured already in 1976 by Garay and Johnson that approximate graph coloring should always be NP complete for every n and n prime at least 3. Right? So if n is equal to 2, then the problem is tractable. So we need to assume n is at least 3. But somehow the state of this conjecture is very open. So for example, it was shown in 1993 that n versus n plus 2n divided by 3 minus 1 is NP complete. This in particular gives you hardness of 3 versus 4. An improvement was shown by Brakes and Guruswamy some years later, n versus 2n minus 2. N versus 2n minus 1 was shown to be NP complete by Bartobul and Korkin-Opschel later. So this in particular gives hardness of 3 versus 5. And asymptotically, the state of the art is exponential. So this result here by Korkin-Opschel, Rockna, and Givny. But as I said before, already 3 versus 6 is open. So it could be that there is a polynomial time algorithm to solve it. Okay, in the second story, this is the situation. So as I said, there is an exponential gap. It's quite funny that it's exponential here. It was also exponential in the first story, the state of the art. So exponential quantum chromatic gap for Hadamard graphs on a limited number of qubits. Also, a line of work focused on finding smaller and smaller examples of graphs exhibiting quantum chromatic gap. So starting from Gaillard, Tapp, and Wolf up to Gottsiel, Sobchuk. Okay, so let me give some ideas of the proof of the first statement. So for every d and for every n, I want to show that there is a graph X whose quantum chromatic number in a d-dimensional space is at most n, but whose classical one is at least 2n minus 1. How to prove it? Well, this essentially comes for free. So you look at the polymorphisms of approximate graph coloring, these objects here, and then you use as a black box a result shown by Brakensik and Guruswamy in the context of approximate graph coloring. So this is the power of using this connection between the two things. So it was shown by them that the polymorphisms of Kn versus Kn prime are trivial precisely when n prime is at most 2n minus 2. And then this automatically gives that the theorem by using the polymorphic approach. So we can just reuse essentially the same structural characterization of polymorphisms for approximate graph coloring to tell something about quantum chromatic gap. Okay, so this means that there is a linear gap between the quantum and the classical chromatic number if the number of qubits, so if D is bounded. So is it possible that the quantum chromatic gap is actually super linear? So this in principle could be possible. And I want to show now very briefly that this is not possible if you restrict the quantum chromatic number to use commuting strategies. So this is what I mean. So let's define chi d of x to be the minimum number of colors that Alice and Bob need to win the game of colors using d-dimensional entangled strategies. So measurements over CD. And up to now, this is the definition of chi d of x, so the quantum chromatic number. But then let's also assume that the measurements commute whenever they correspond to adjacent vertices. So this is something that is very natural to require for CSPs that are not binary, so on higher arity. notice that here I'm putting some extra constraints. So the quantum chromatic number, as I defined it before, is small, is never bigger than this new notion. So chi d is less than or equal to chi tilde d, which is less than or equal to chi. Okay, so what we showed in a recent paper with Bana, Kojic, and Tuluyeki is that for every d and for every x, the classical chromatic number of x is at most some constant factor, so a constant depending only on d, times the d-dimensional quantum chromatic number using commuting strategies. In other words, this means that if you use this type of quantum chromatic number, so if you also enforce commutativity between the projectors, the classical chromatic number cannot be too big. It cannot grow, for example, exponentially in the quantum one. The gap is at most linear. Okay, so I will not tell the proof, but the proof comes from somehow a different problem. So a problem that we were studying on classical simulation of perfect entangled strategies. So this is the setting somehow. So I have, again, the same question as before, the coloring game or the homomorphism game. So again, Alice and Bob strategize, but this time they're not completely, there is some communication channel, right? So it is possible that Alice and Bob communicate a little bit during the game. And the verifier asks Alice, what's the color of XA? And Alice replies, but after replying, she can send some bits, some classical bits of information to Bob, so a limited message. And now Bob can answer to his question by taking into account the message. Right. So the goal now is to understand what is the minimum number of communication bits. So what is the size of the channel that is needed in order to simulate a perfect entangled strategy? And this is a problem from communication complexity, quantum communication complexity. Okay, so what we are showing is that it's always possible to simulate a d-dimensional perfect entangled strategy using a communication channel, a classical communication channel whose size depends on d, so on the number of qubits, and on y, so on the template, but it does not depend on x. And essentially, the proof of this gives for free a minion homomorphism from the quantum minion to the polymorphism minion of approximate graph coloring, n versus m, where m is some constant, so 2 plus 0.1 power the dimension of h minus 1 times n. And this means that the pair Kn, Km has no quantum advantage over Cd, which is exactly a synonym of the statement of the theorem. Okay, I think I have 5 more minutes, so I'll try to be fast. So the last part I want to tell about what happens in the case where I have unlimited, unbounded quantum resources, right? So let's go back to the story. This is now a bit chaotic, but it's the last time I will mention this. So I want you to focus on this rectangle here. So already in 1972, it was shown by Karp that SAT and other problems are NP-complete. So SAT is the problem of understanding satisfiability of a Boolean formula. And it was later shown in a masterpiece of complexity theory, the PCP theorem, that even the gap version of SAT is NP-complete, right? So even if I just want to distinguish formulas that are perfectly satisfiable from those that are highly unsatisfiable, this is still NP-complete. And this theorem here, PCP stands for probabilistically checkable proof. So but somehow this version here is the one that we are going to need, and is equivalent to the original version about multi-prover systems. So this theorem here gave us a way of essentially it opened the era of hardness of approximation. It gave us a way to find optimal thresholds of at which we can approximate CSPs and other problems. So for example, optimal thresholds were found for free SAT or free XOR, but also for non-CSPs such as click and set cover. But for some other problems, the optimal gap was not found. And this is what pushed Cott to define or to look at a stronger version of PCP called unique games conjecture, or its D2-1 variants, which essentially states that a gap version of another CSP, which is very structured, so it's a label cover instance with 1-to-1 or D2-1 constraints, is still NP complete. So I'm not going to go into details on this, but conditional to this conjecture here, many more optimal approximability results were found. For example, for max cut, vertex cover, and also approximate graph coloring. Okay, so ideally, we would like to do something similar in our setting. Okay, so a bit more precisely, we want to turn the source of hardness, which is the PCP and the unique games conjecture, into a source of quantum advantage. Let's see how to do it. So we start from the D2-1 conjecture, which states that for every epsilon, if I give you an instance of D2-1 label cover on some suitably large alphabet, it is NP complete to distinguish perfectly satisfying assignments or to distinguish whether there exists a perfect satisfying assignment from the fact that there is no assignment satisfying at least epsilon fraction of the constraints. This is the quantum analog. So for every epsilon and for every k, there exists a label cover instance on some suitably large alphabet such that phi admits a perfect quantum strategy, but the classical value, so the biggest probability that a classical assignment is satisfiable is at most epsilon. And here I'm also assuming that I have K compatibility, which is a technical notion. Essentially, it means that the projectors corresponding to vertices in the strategy that are close must commute. Okay, so this is the analog of the D2-1 conjecture. And let's now look at the analog of inapproximability of linear equations, right? So this is a result. This is not a conjecture. This is a theorem due to Hosted coming from the PCP theorem, actually, saying that it's hard to distinguish instances of linear equations that are almost satisfiable, right? So having the sat of phi at least 1 minus epsilon from those that are highly unsatisfiable, right? So sat of phi is smaller than some S star. In fact, we can take S star to be 1/2 plus epsilon. And also in this case, we can define a quantum advantage notion of this, which looks like this. So for every integer n, there exists some regular freak source system, which means it's a system of linear equations having free variables per equation plus some additional technical properties, whose classical SAT value is at most S star, but such that if I consider a suitable n-fold repetition of the game, this admits a perfect quantum strategy. So again, this definition is a bit technical, but it captures in the quantum advantage setting the inapproximability of linear equations. And now the result is that conditional to conjecture A, there is a free versus arbitrary quantum chromatic gap, right? So for every n, there is a graph whose quantum chromatic number is free, but whose classical chromatic number is larger than n. And conditional to conjecture B, again, for every n, there is a graph whose quantum chromatic number is either 3 or 4, but the classical one is arbitrary, so it's larger than n. And in the next 1 or 2 minutes, I will just give the idea of the proof. So the idea was to use a very abstract class of transformations in graph theory and in CSP theory, known as Poulter functors, right? So Poulter functors are pairs of functors between categories of relational structures. I will not give the definition. I will just tell a few examples. So let's say that I have a digraph G, and I consider the following transformations. So the first transformation takes a graph X and returns the direct product of X and G. The second transformation takes a graph Y and returns the exponential digraph Y power G. Okay. Another example, I have two digraphs X and Y. Lambda of X is obtained by taking X and replacing every vertex with a new edge, X1, X2, and then I identify X2 and Y1 whenever XY forms an edge in the original graph. And gamma Y is just the line digraph of Y. So the vertices are edges and the edges are pairs of consecutive edges. Right? So these are somehow classic transformations in graph theory, the key point is that they satisfy a thin adjunction relation, which is the following. So if lambda x maps to y precisely when x maps to gamma y. So both these pairs and many others satisfy this adjunction relation here. And in fact, one can show that all Poulter functors do satisfy this. Okay, so the first step of my proof was to show that this also holds in the quantum world. So there exists a quantum version of Poulter adjunction, modulo some technical stuff. So we need to assume that the Poulter templates are good enough. And in fact, there are two different definitions of good enough for the two directions of the implication. But modulo this, lambda x admits a quantum homomorphism to y if and only if x admits a quantum homomorphism to gamma y. And then one looks at the chain of classical reductions that are used in hardness of approximation to go from gap label cover or gap XOR to approximate graph coloring. And there are multiple steps that needs to be handled. So some of them are Poulter functors, some of them are similar to and can be handled essentially in the same way, but they're not exactly Poulter functors. So each of these steps requires some ad hoc technique. But the whole point is to use quantum Poulter adjunction to show that one can transfer, instead of approximation hardness, quantum advantage from left to right. And so starting from the conjectures about label cover and trick XOR, one ends up with a large unbounded quantum chromatic gap. Okay, and I think my time is finished, so I will stop here. Thanks a lot.
Thank you, Lorenzo, for the next. Do we have questions for Lorenzo? You might have mentioned it, but I missed it earlier. You have the result about there exists graphs with the chromatic number is at least 2n minus 1, but the quantum version is at most n. Do you have some concrete graph family for that?
Yeah, no, this is somehow, this is a good question, because one, so somehow all other results like this that I know about, they come from explicit descriptions of graphs having a large gap.
Yeah.
And somehow this proof here and the proof of all the results that I showed you in this last part are very non-constructive. So they come from a property of polymorphisms, but they don't tell you actually how to build the instance. So there is no, I have no example of a graph exhibiting this gap.
Yeah, thank you. This might be a silly one. You have always been fixing some graph y in the game. Is there some interesting game where you fix x but change y or something?
Yeah, this is another actually very, very interesting question, because somehow from a quantum advantage perspective, it makes sense. So it is symmetric. So you can fix x and ask whether x is quantum advantage and define this as the existence of some y for which there is a perfect quantum but not classical strategy. But from a complexity point of view, this question cannot be asked, because all this, so if you fix x, then the corresponding CSP is always solvable in P. So these are called left-hand side CSP, and they're usually studied for families of graphs X, because if you fix just one, then the problem is always in P. And but more in general, this algebraic approach only applies where you fix the template Y and let X be the instance. So there are some other tools that can be used, tree width, bandwidth. So there are some more graph theoretic notions that allow you to capture the hardness for families of graphs that you fix as your X, but these do not seem to apply to this quantum advantage setting. So yeah.
Thank you. It's a Lorenzo for the nice talk again.
Thanks a lot.